In this video, we present our paper, PlankAssembly. We tackle a long-standing problem in the computer design field, namely 3D object reconstruction from 3 orthographic rules. 2D engineering drawings are commonly used in product design and manufacturing industry. Over the past few decades, 3D reconstruction from 3 orthographic rules has been extensively studied. Almost all existing methods follow a bottom-up approach that consists of several key steps. First, generating 3D vertices from 2D vertices. Second, generating 3D edges from 3D vertices. Third, generating 3D faces from 3D edges. Fourth, generating 3D models from faces. These methods guarantee to find all solutions that match input views. Unfortunately, in practice, designers would deem a drawing good enough as long as it converts their ideas. Hence, some entities may be erroneous or missing when the inputs contain some error lines as we highlight in blue color here. Existing approaches fail to recover all 3D blocks, resulting in a failure of the projection verification in the final solid reconstruction step. In our work, we focus on cabinets and we develop a simple domain-specific language for them. A cabinet is typically assembled by a list of plank models. Each plank can be represented by an X-size aligned cuboid with 6 degrees of freedom. However, in practice, instead of specifying numerical values for all the coordinates, designers frequently use the attachment operation. Our language also supports this operation. As the shape program commands of a simple cabinet shown here, we only specify the numerical values for the coordinates that do not attach to any other coordinates. Otherwise, the coordinate is a pointer to another cuboid to which it attaches to. With the help of PlankAssembly shape program, we cast this problem as a sequence-to-sequence problem. We assume the input consists of lines in joints, and our goal is to output 3D cabinet models described by the shape program. We use the standard transformer blocks as the basic blocks of our model, and use the tension mechanism to learn the mappings between the input line joints and output shape program. We adopt a point network which generates a point distribution over the output sequence. At the same time, transformer decoder also outputs a probability distribution over a fixed length vocabulary set of quantized coordinate values. Instead of directly comparing these two distributions, we follow point generator networks and introduce an attachment probability to weight these two distributions. The final distribution is obtained by the concatenation of two weighted distributions. We create a large-scale benchmark dataset with 26,707 cabinets for this task, taking advantage of access to a large repository of cabinet furniture models from Kujiale. The figure reports the F1 scores from 0% to 30%. For completeness, we compare two variants of traditional pipeline figure. In the first variant, we enforce the reprojection verification step during reconstruction, and we ignore it and directly use the union of blocks as the solution in the second one. On clean inputs, the first variant achieves a slightly higher F1 scores than the second one. However, this variant isn't applicable to noisy inputs. Comparing our approach with the second variant, our approach is much more robust to inputs in noises. Specifically, performance only slightly drops from 91.75% to 90.14%, as the noise level increases from 0% to 30%. Also, the performance of the second variant decreases quickly. These figures visualize some 3D reconstruction results from clean inputs of the two methods. Our approach correctly reconstructs all 3 objects, whereas the traditional pipeline fails on the last 2 objects. Specifically, for the second object, the traditional pipeline produced multiple solutions, and an incorrect one is selected as the final output. And for the third object, the traditional pipeline fails to produce any result within 5 minutes. Here we show results from input with noise level of 10%, 20%, and 30% respectively. The traditional method fails on all 3 objects. In particular, it fails to find any valid blocks for the cases with a noise level of 30%. In contrast, our method correctly reconstructs all objects. Here is the visualization of model while scaling along the x-axis or moving a single plank model. All code is publicly available at GitHub. Thanks for your attention.